There's dew on the bench beside me. Not heavy, just that faint, cold damp you feel if you press your palm flat and hold it there. The park is empty, has been since I got here. And the silence isn't uncomfortable exactly, it's more like the silence of a room before someone walks in. That specific, loaded kind of quiet. I don't know why that feels like the right place to start. Maybe it doesn't. But something about being here before the city wakes, before there's anyone to ask anything of the morning, makes me think about questions, where they come from, what has to already exist in the world before a question's even possible. If you're still awake, that's okay. If you're nearly gone, that's okay too. Nothing here requires your full attention. You might want to find the sleepy physicist's other videos after this, or tell someone who struggles to sleep that these exist. Either way, gently, no pressure at all. There's a thing that happened in the history of physics that I keep coming back to. Not because it's dramatic, it isn't, really, but because of the gap. The strange long gap between when something was observed and when anyone let themselves be bothered by what it meant. The double slit experiment. You might have heard of it, and if you have, you probably heard it in a context that made it sound settled, explained, filed away under quantum weirdness with a little bow on top. It isn't settled. It's one of those results that gets more uncomfortable the longer you sit with it, not less. But for a while, for decades actually, physicists sat with it and mostly looked away from the part that didn't make sense. That's not a criticism. That's just how knowledge moves. Sideways sometimes, reluctantly. The experiment itself is old. Thomas Young did a version of it in 1801, though he was working with light and he wasn't thinking about any of what we're thinking about now. He was just trying to settle an argument about whether light was a wave or a particle. And he did settle it, sort of. He showed that light made an interference pattern when passed through two slits, which is exactly what waves do and exactly what particles don't. So, wave, done, except it wasn't done, because in the early 20th century things got strange. Physicists started doing the same experiment. Same basic geometry, two slits, a screen, but instead of light, they used electrons. And the electrons also made an interference pattern, which shouldn't have been possible because electrons are particles, they're things. They have mass. You can't cut an electron in half and send one piece through each slit. But the pattern appeared anyway. And at this point I think the right response would have been a long collective pause. A kind of wait, hold on, what is this? But the early quantum pioneers were busy. They were building the formalism of quantum mechanics, and the formalism worked, it predicted the right answers. And there's a particular kind of intellectual relief that comes with a working formalism. You stop asking why it works and start using it. That's human. Completely understandably human. The question, the real question, the uncomfortable one, got set aside. It didn't go away though. It just sat there. In the equipment, in the math, in the results that kept appearing every time anyone ran the experiment again. Here's the part that took the longest to reckon with. When physicists sent electrons through the double-slit apparatus one at a time, meaning they weren't sending a stream of electrons where interference could theoretically happen between separate particles, the pattern still built up, slowly. Dot by dot, each electron landing somewhere on the screen seemingly at random. But over time, those dots didn't scatter evenly. They clustered. They formed the same fringes, the same interference pattern, arriving one particle at a time, which means each electron interfered with itself. And the only way that works, the only story you can tell that makes the math make sense, is that each electron somehow travelled through both slits simultaneously. That before it landed, before it became a dot on a screen, it existed in a kind of blurred, spread-out state that let it take every available path at once and interfere with its own trajectory. A position, that's the word. But the word doesn't really do anything for you the first time you hear it. It sounds like a technical term for a thing that's been explained. It hasn't been explained. It's been named. Those are different. The part that broke me a little, or not broke, that's too much. The part that left a small, quiet crack in how I thought about things came later. When someone decided to find out which slit the electron actually went through, just to check, just to know. They put a detector near one of the slits. Small, careful. They didn't want to disturb anything. They just wanted to observe, and the interference pattern disappeared. Not degraded, not shifted slightly. Gone. The electron started landing in a different pattern, the kind of pattern you'd expect from particles going through one slit or the other. No interference at all. As if they'd forgotten how to be waves. As if knowing which way they'd gone changed what they'd done. That's the question this whole video's sitting with. How does a particle know it's being watched? Not as a koan. Not a mysticism dressed up in physics. As a real, technical, frustrating question that physicists actually grapple with. What is it about the presence of a detector? About the possibility of witch path information existing somewhere in the universe that changes how an electron behaves? Is it the physical disturbance of the measurement? Is it something about information, about knowledge, about the fabric of what's allowed to stay uncertain? We're going to spend some time with this, slowly, but right now I want to stay in the gap between 1801, when Young did his experiment and called it done, and the decades of quantum mechanics that followed, when everyone sort of knew something was off and mostly let the math do the talking. There's something worth sitting with there, not as a failure, it isn't, but as a recognizably human thing. It's hard to ask a question whose implications you can't yet handle. Not intellectually hard. Emotionally hard maybe, or maybe structurally hard. The question requires concepts that don't exist yet. Language for things that haven't been named. A comfort with uncertainty that takes a long time to build. The double-slit experiment was asking something that wouldn't fully be heard for almost a century. Something about the relationship between what exists and what is observed. Between what happens and whether anything registers that it happened. That's either a very strange physics problem or a very old philosophical one, or, and this might be where it gets genuinely interesting, it might be both, tangled together in a way that neither field is entirely comfortable with. I don't know if that tangle ever fully comes loose. I'm not sure it should. The dew is already drying, sun's almost up, and the question is still there, in the grass, in the quiet, patient in the way that old unsettled things tend to be patient, like it knows we'll get back to it. We will. The screen at the far end of the apparatus is still there, and the pattern it shows, the one that changes depending on whether anything is watching, is what we'll start pulling apart next. The barrier is just a wall. That's worth saying plainly before anything else. It's a physical object, metal usually in the lab versions, with two narrow gaps cut into it. Not complicated, not elegant, the kind of thing you could hold in one hand and not find particularly interesting. And yet this unremarkable object, this small flat piece of matter, with two slots in it, has been sitting at the centre of one of the strangest unresolved arguments in the history of physics for over 200 years. Two slits, a source on one side, a screen on the other. That's the whole apparatus. Young's original experiment used light. Sunlight, actually. He let a thin beam into a darkened room and directed it toward a card with two pinholes. What landed on the wall behind it wasn't two bright spots. It was a series of alternating bright and dark bands spreading out sideways, wider than the holes themselves. Fringes, The kind of pattern you'd get if you dropped two pebbles into still water at the same moment and watched the ripples from each one meet and interact, adding together where their peaks aligned, cancelling where one's peak met the other's trough. That cancelling is the thing. The dark bands aren't where light was blocked. They're where light arrived from both holes and the two contributions subtracted each other to nothing. That only works if light is a wave. Particles don't do that. Two bullets don't cancel each other out. Two streams of sand don't produce dark stripes on the wall behind them. Only waves interfere, so light is a wave. Young was pleased. The experiment was considered settled. Then the 20th century arrived and things stopped being settled. Electrons through the same setup, same geometry, same logic. Two slits, a detection screen, a source of particles fired one direction, and the result that should have just shown two bright bands where the electrons piled up after passing through one slit or the other, was an interference pattern. Fringes again, the same alternating structure, the same dark gaps where apparently electrons weren't arriving, the same strange, unnecessary beauty. It was confusing in a way that's hard to fully reconstruct now because we've had a century to get used to the confusion. But think about what it meant. An electron is not a wave in any ordinary sense. It has a specific mass, 9.1 times 10 to the negative 31st kilograms, which is genuinely nothing. But it is a specific, measurable nothing. It carries a definite charge. It can be deflected by a magnetic field. It lands on the screen as a single discrete point, not a smear. Everything about it behaves like a particle, except for this, except for the pattern it leaves behind when many of them have passed through. The pattern is not what particles leave, the pattern is what waves leave. And then came the version of the experiment that really shouldn't be allowed to be true. Electrons sent through one at a time, not a stream, one, then another, each fired individually, each landing separately on the screen. The screen records each hit as a dot. For a while the dots look random, no pattern, just individual points scattered across the surface. You watch for a while and you don't see anything organizing, and then you keep watching, and the dots accumulate, and the clusters start to appear, and eventually, slowly, patiently, over thousands of individual electrons, the interference fringes are there, each electron contributing one dot, no electron interacting with any other, the pattern emerging anyway. This is the moment that demands something from you. Not an explanation, not yet, just a genuine pause. Because there's no story you can tell about individual particles passing through one slit or the other that produces this result. If each electron went through the left slit, it would pile up in one band. If it went through the right, another. Some mixture of both would give two bands, not fringes, not this spreading, alternating structure with its precise dark gaps. The pattern requires that each electron, somehow in some sense that the word somehow doesn't really cover, went through both slits, or rather, that before it landed, before it became a definite dot in a definite place, it existed in a state that wasn't localized to one path. A state that was, in the precise mathematical sense, spread across both possibilities simultaneously. Superposition. The electron in two places at once, or more carefully in no definite place at all until it arrived. That's the central metaphor this chapter is going to let sit. The electron is a question that hasn't yet been answered. Not a particle travelling in secret through one slit. Not a wave in any physical medium. A question, an unresolved, suspended question, moving through the apparatus in a state of genuine ambiguity, and the interference pattern is what an unresolved question looks like when you accumulate enough of them. It's not a perfect metaphor. Metaphors never are. but it might be useful. Here is what the math says without softening it too much. The electron is described before measurement by a wave function. This function isn't a description of where the electron probably is, it's a description of the electron's actual state, a real physical thing, or close enough to real that the distinction barely matters for now. The wave function spreads, it passes through both slits. The two portions of it interfere with each other on the far side of the barrier, and that interference determines the probability of the electron landing at any given point on the screen. High probability where the wave function's peaks add up, near zero probability where they cancel. The electron lands where it's most likely to land. Over many electrons, the probability distribution becomes visible as a pattern, the interference pattern. So the strange thing, the deeply strange thing, isn't that the math works. The math works beautifully. The strange thing is what the math is describing. A particle with the definite mass and charge and eventual position that nonetheless, before it arrives, has no definite position at all. That travels not through one slit or the other, but through both, in the only sense that the physics allows us to use that word. The barrier is still just a wall, two gaps, plain metal, but what passes through it is something the word particle was never quite designed to handle. Next, someone decided that wasn't enough. They wanted to know which slit, not just statistically, definitely, for each electron, which one. And that decision, that reasonable, curious, seemingly harmless decision, is where the experiment becomes something else entirely. Start with what interference is not. It is not two things colliding. It is not one thing overpowering another. It is not a compromise, not a blend, not an average. Interference, the kind that produces fringes, that produces those alternating bands of presence and absence, is something more specific than any of those. It is what happens when two versions of the same thing arrive at the same point and the universe has to decide mathematically whether they add or subtract. Waves do this. Water waves, sound waves, light waves. Wherever two of them meet, the result at that meeting point is the sum of both, which means if both waves are peaking at the same moment, you get a bigger peak, and if one is peaking where the other is troughing, you get nothing. Cancellation, not destruction, not loss, just nothing because they balanced. That much is classical. That much belongs to the physics of the 19th century, and it is not, on its own, particularly strange. What is strange is that the electron does this with itself, not with another electron, with itself, with its own possibilities. This requires a certain kind of patience to sit with, because the instinct is to reach for an analogy that makes it feel manageable, to say it's like a wave, to say the electron is smeared out, to reach for something familiar. But the familiar thing always falls short, and the falling short matters. The electron isn't a wave in any medium. There is no quantum fluid it's rippling through. The wave function, the mathematical object that describes the electron's state before measurement, is not a physical wave in the way that a water wave is physical. It doesn't move through space the way water does. It is, in some sense, that physicists still argue about in conference rooms that smell like stale coffee and marker fumes, a description of possibilities, of what could happen, weighted, precisely, by probability, and it is those weighted possibilities that interfere with each other. Not two electrons, not two physical things, two branches of the same potential, arriving at the same screen from different directions, and combining according to rules that are exact and unforgiving, and produce, when enough particles have gone through, a pattern of breathtaking regularity. A kid just appeared at the far end of the park, maybe 8 years old, kicking a football in no particular direction, completely alone in all this early morning quiet. Not looking for anything, just moving. There's something in that which I want to hold for a second before continuing. The wave function doesn't know where the electron will land. That's not a gap in the theory, it's the content of the theory. The theory is not saying we lack the tools to track the electron's actual path, it's saying the electron does not have an actual path. Before it lands, there is no fact of the matter about where it is. There are only amplitudes, complex numbers in the mathematical sense with magnitude and phase, assigned to every possible position, and those amplitudes evolve according to the Schrödinger equation in a way that is perfectly deterministic, perfectly smooth, until the moment the electron arrives somewhere and one possibility becomes real. The interference happens during that smooth deterministic evolution. The two portions of the wave function, the part that went through the left slit, the part that went through the right, travel different distances to reach any given point on the screen. Different distances mean different phases. Different phases mean at some points the amplitudes add and at others they cancel, and where they cancel the probability of the electron arriving is 0. Dark band, absence. No electron gets there, not because something blocked it, because the two possible paths of its own wave function subtracted each other out. This is what interference actually requires. Not two objects, not two particles. A single quantum system with at least two available paths and a wave function coherent enough, undisturbed enough, to maintain a definite phase relationship between them. That word, coherent, is load-bearing. It means the two portions of the wave function are still in a precise trackable phase relationship with each other, like two musicians playing the same note in exactly the right timing, not approximately, not nearly, but exactly, so that when they arrive together their contributions interfere predictably. The moment the phase relationship is disrupted, the interference degrades. The fringes wash out. The pattern softens and then disappears into something that looks much more like what you'd expect from particles. And disruption, it turns out, is easy. Almost anything can do it. A stray photon, a vibration, an interaction with the environment that carries away information, even a tiny amount, even unintentionally, and about which path the electron took. No, perhaps that's not quite it, or not the full picture. It's not just disruption in the physical sense. It's something more specific than a jolt or a nudge. It's about whether the environment now contains, encoded somewhere in its state, a record of which way the electron went, whether the information exists, even if nobody reads it, even if it disperses into the walls and the air and the machinery and is practically inaccessible to anyone. If it exists, the coherence is gone, and the pattern with it. The kid kicked the ball wide and it rolled into the hedge. He stood there for a moment looking at it, then walked over slowly and pulled it free. There was no drama in it. It just happened. The ball went one way, then it was retrieved, and the morning continued. That image keeps returning to me, not for any precise reason, just something about watching a thing move through space with a definite trajectory, a definite arc landing in a definite place. Classical, perfectly reassuringly classical. You could, in principle, know exactly where that ball would go if you knew the force and angle and air resistance. The path exists, the ball is somewhere specific at every moment. The electron before measurement isn't. That's the gap, not a matter of measurement precision, a matter of what the universe at that scale actually contains. The interference pattern is the evidence for that gap. It is what a genuinely unlocalized thing looks like when you gather its statistics over time. Not randomness, not noise, but a precise structured imprint of its own internal possibility space. The dark bands aren't gaps in the electron's journey. They're the places the electron could never arrive, because its own wave function made arrival there impossible. The coherence required for this to work is, in everyday terms, extraordinarily fragile. At room temperature, electrons in a conductor interact with their environment billions of times per second. the coherence is destroyed almost instantly. The interference, the quantum behavior, never gets a chance to appear. This is part of why quantum effects feel so remote from ordinary experience. They aren't remote in principle. They're remote because the conditions that allow them to persist are genuinely difficult to maintain. Cold, isolated, undisturbed. The experiment has to create a kind of stillness that doesn't occur naturally at human scales. 2 slits, a single electron, a coherent wave function passing through both, and a screen that records patiently where each one lands. That's all it takes, as long as nothing at all, carries away the information about which path was taken, which is what makes the next step so quietly devastating. Because someone wanted to know, they wanted to add a detector, to place something near one of the slits that would register, for each electron which way it went. Not to disturb anything, not to interfere in the physical sense, just to know, and knowing, as it turns out, was enough. The detector doesn't look like much. In the actual lab versions of this experiment, the ones run since the 1970s and refined considerably since, the witch path detector is often a carefully tuned laser field placed near one of the slits, designed to scatter a single photon off the electron as it passes. 1 photon, the smallest possible interaction, the minimum amount of looking that physics allows, and even that is too much. The reasoning behind adding a detector seems almost embarrassingly sensible. Here is a particle. It is going through an apparatus with 2 openings. Surely it goes through one or the other. Surely there is a fact, hidden from us perhaps, but real, about which slit each electron uses. The interference pattern is strange, yes, but maybe it's strange for boring reasons. Maybe the electrons are interacting with each other in ways we haven't accounted for. Or maybe the wave function is just a calculational tool that doesn't correspond to anything physically real, and underneath it all, the electrons are doing something straightforward that we're simply not tracking. The detector would settle it. Watch which slit each electron uses, build up statistics, and then the interference pattern would either remain, proving the electron really does something non-local, something genuinely spread out, or it would vanish, and some simpler explanation would present itself. What happened was neither of those things, not quite. The interference pattern vanished, but no simpler explanation presented itself. The electrons, once their path was monitored, began landing in a distribution that looked exactly like what you'd expect from classical particles, 2 rough bands behind the 2 slits. No fringes, no alternating structure, nothing suggesting wave behavior at all. The witch path measurement worked. Each electron registered at one detector or the other, left slit or right slit, never both. Definite, clean, particle-like, and the pattern on the screen reflected that. The electrons behaved from that point forward as though they had always been particles, as though the question of superposition had never applied to them. That part is strange enough, but the part that took longer to absorb, and still hasn't been fully absorbed if I'm honest, is that the disappearance of the pattern wasn't caused by the physical disturbance of the measurement, at least not in the way you'd first assume. The obvious explanation, the one that feels satisfying and mechanical and livable, is that the detector kicked the electrons, physically disturbed them. A photon bouncing off an electron imparts momentum, changes the trajectory, adds uncertainty to the position, and that uncertainty smears the interference pattern away. Heisenberg's uncertainty principle. The more precisely you know the path, the less precisely you can know the momentum, and messed up momentum means messed up interference. Clean, almost too clean. Physicists tested this. They designed experiments where the physical disturbance was carefully controlled, where the momentum kick from the witch path measurement was kept small enough that by the uncertainty principle accounting, it shouldn't have been sufficient to wash out the fringes, and the fringes washed out anyway. The pattern disappeared not because the electrons were kicked off course, but because the witch path information existed somewhere, in the detector, in the photon that scattered, in the state of whatever physical system made the measurement. The information, not the kick. The information. This is the point where the experiment stops being about waves and particles and starts being about something else. Something that doesn't have a clean name yet. Or rather, it has several names depending on which interpretation of quantum mechanics you find least uncomfortable, and none of them feel entirely right. Here is the clearest way I can put it, and I'll say up front that even this framing is probably not quite right, or not complete, or is right in a way that generates more questions than it closes. An electron maintains its superposition, its ability to exist across both paths and interfere with itself, as long as no information about its path exists anywhere into the physical world. Not in a human mind, not in a conscious observer, in the physical world, in the state of any system it has interacted with. The moment a witch path record is created, even if it's just one photon in a state that could in principle be read, even if nobody ever reads it, even if it disperses into the environment and becomes practically inaccessible, the superposition is gone, the interference is gone, the screen shows two bands. There's an experiment, several actually, but one in particular, where the witch path detector was set up, but then the path information was deliberately scrambled before it could be read. Not erased from reality, just made inaccessible, mixed into noise. In those versions, the interference partially recovered, not fully. The degree of recovery corresponded almost exactly to the degree of remaining path information in the system. The less the universe knew, the more the electron interfered. I find that sentence difficult to say without slowing down. The less the universe knew, as if knowledge, not human knowledge, not conscious knowledge, but some physical analogue of knowledge, some residue of correlation between systems, is the variable that governs whether quantum behavior persists. That's a strange variable. It doesn't appear in classical physics anywhere. In classical physics, things happen regardless of whether anything records them. A ball falls whether or not there's a camera watching. The trajectory is real either way. The record is incidental. In quantum mechanics, the record is not incidental. The record is, and I want to be careful here, because this is the edge of what the physics actually says versus what it's tempting to say. The record is physically consequential. Its existence changes what the particle does, not what we know about what the particle does, what it does. The detector near the slit didn't need to be connected to a computer, didn't need to trigger an alarm, didn't need to be read by anyone in the lab. Its mere physical existence, its being in a state that was correlated with which slit the electron used, was enough to collapse the superposition, to make the electron choose. Or, no, choose is wrong. That implies something internal to the electron, some decision being made. The electron doesn't choose. What happens is more passive than that, and more absolute. The coherence between the two path possibilities simply ceases to be maintained. The phase relationship between them, that precise, fragile timing that allowed the wave function to interfere, is broken by the entanglement between the electron and the detector. The two portions of the wave function can no longer combine cleanly. The interference terms in the probability calculation go to zero. The math is exact. The conceptual picture underneath the math is still, after a century, not agreed upon. What I keep coming back to, and this is opinion, not physics, is how little the detector needs to be. How minimal the act of knowing is in physical terms, and yet how total its consequence. One photon, one correlation, one tiny fleeting entanglement between the electron and something else. And the whole quantum behavior is gone, not suppressed, not weakened, gone, as completely as if it had never been possible. The barrier is still there, the two slits are still there, the electron still goes through. But the screen shows something ordinary, something that requires no new physics to explain, something that looks from the outside exactly like a particle behaving exactly like a particle should. As if the strangeness only exists in the absence of anyone looking. Whether that framing is literally true or just a useful way of gesturing at something the language hasn't caught up with yet, that's a question the experiment cannot answer. It can only demonstrate with patience and precision and a consistency that has never once failed across every version of this test ever run, that the looking matters. That the attempt to know which path is never neutral, it never just watches, it always changes what it sees. The first explanation feels good in the body. That matters, actually. The way a physical explanation settles differently than an abstract one. When someone tells you the detector disturbed the electron, something in you relaxes because disturbance is something you've felt. You've felt it when a door opens in a quiet room and the air shifts. You've felt it in the way a conversation changes when someone new walks in. Disturbance is causal, local, mechanical. It connects to a long chain of experiences that tell you things affect other things by touching them, pushing them, transferring something across the gap between one object and another. That's how the world works at the scale you live in. So when the interference pattern disappears after measurement, and someone offers disturbance as the reason, there's a quiet comfort in accepting it. The explanation is, the detector had to interact with the electron to detect it. A photon bounced off it. That photon carried momentum, and the transfer of that momentum nudged the electron's trajectory in an unpredictable direction, and enough unpredictable nudges across enough electrons blurred the interference pattern into noise. It's clean, it's physical, it connects to things you already understand. It's also not the whole story. And it took several decades and some genuinely clever experimental designs to demonstrate exactly where it falls short. The problem with the disturbance explanation isn't that it's wrong in some obvious way. Is that it's too small, too local. It accounts for some of the pattern's disappearance. Physical kicks do add uncertainty, and uncertainty does degrade coherence. But when experimenters started controlling for the disturbance precisely, keeping the momentum transfer from the detector small enough that Heisenberg's uncertainty principle said it shouldn't be sufficient to wash out the fringes washed out anyway, every time. Without exception, the disturbance was below the threshold required to explain the effect, and the effect was total. That gap between how much physical disturbance occurred and how completely the interference disappeared is where the real question lives. Marlon Scully and his colleagues worked through versions of this in the 1990s, designing what they called quantum erasure experiments, and what their setups made vivid, more vivid than any purely theoretical argument could, was that the interference pattern's fate was tied not to the physical kick of the measurement but to whether the witch path information survived. They used atomic systems, microwave cavities, setups where the witch path information was stored in internal states of atoms rather than in flying photons, and they showed that you could tune the disturbance independently of the information. You could kick the electron hard without creating a witch path record, and the fringes survived. You could leave the electron almost entirely undisturbed, but create a clean witch path record, and the fringes vanished. The variable that controlled everything wasn't force, it was information. That shift from force to information as the governing variable is the kind of thing that sounds like a philosophical nuance but is actually a full reclassification of what's happening physically. Because force is something you can point to. Force is a transfer of momentum, a vector, a measurable push from one thing to another. Information is, and here the language starts to strain, starts to reach for things it wasn't quite built to carry. Information is a correlation, a record, a state in one system that is entangled with, that carries a physical imprint of, a state in another system. The detector doesn't ruin the interference by pushing the electron off course. It ruins it by becoming correlated with the electron's path, by entering a physical state that is different depending on which slit the electron used, by creating a relationship between its own state and the electron's state that, in principle, could be read, even if nobody reads it, even if it disperses into the environment and becomes practically inaccessible. The correlation is there, and its presence alone is enough. The information exists, and that is sufficient. The information exists. 3 words that are either a statement about physics or a statement about something more fundamental than physics, and it's genuinely difficult to know which, and I'm not sure the difficulty resolves, even after sitting with it for a long time. Because here is what it seems to be saying: the universe tracks things, not consciously, not intentionally, but physically, in the only sense that matters at this level. The universe maintains correlations between systems that have interacted, and those correlations are real, and they have consequences that extend beyond the interaction itself. The electron going through the slit leaves a mark on the detector, and the mark changes what the electron can do afterward, even if the mark is never examined, even if it fades into thermal noise, even if every practical trace of witch path information is gone from any human accessible record. The physical correlation persists in ways that we can't always follow, but the mathematics insists are there. There is a word that comes up here: observer. And it has caused, I think, more confusion than almost any other term in the popular understanding of quantum mechanics. More confusion and possibly more unearned mysticism, because observer in quantum mechanics has never meant what it sounds like it means. It has never required a mind, never required consciousness, never required a human being in the room or anywhere near the apparatus. And yet the word sits there loaded, in textbooks and articles and documentaries, trailing implications that the physics never actually licensed. The question of what an observer is, what it means physically for something to count as an observation, is not fully settled. I want to say that clearly, and then leave it sitting here, slightly unresolved, because forcing a closure on it would be dishonest. What the experiments show is that any physical system capable of registering a state difference, any system that ends up in a different state depending on which path the electron took, functions as a witch path detector. It doesn't need to be switched on by a human. It doesn't need to be read. It doesn't need to be large or sophisticated or intentional. But whether that fully answers the question of what an observer is, whether it dissolves the question or just renames it, I'm not entirely sure. What the Disturbance story got right was the intuition that measurement is never passive. That's real. That's physics. You cannot extract information from a quantum system without that system being changed by the extraction. Not because our instruments are clumsy, not because we lack precision, but because the physics of information at quantum scales makes passivity impossible. To know is to interact. To interact is to entangle, and entanglement, once created, is not a footnote. It is the whole story. What the Disturbance story got wrong was the mechanism. It pointed at the push when the relevant thing was the print, the physical imprint, the correlation that remains after the push is over, whether or not anything reads it, whether or not the push was large enough to matter kinematically. The electron cares, if we're allowed to use that word, and we're probably not, but it comes close enough. The electron cares not about being touched, but about being known, about whether the universe, after the interaction, is in a state where which path information is recoverable in principle. If it is, no fringes. If it isn't, the fringes return, and the extraordinary quiet thing, the thing that takes a while to feel the full weight of, is that this has been tested. Not just theoretically argued, experimentally tested in labs with real particles and real detectors and real screens many times by many different groups, and it has never come out differently. The information, not the disturbance, is what governs the outcome every single time. The universe, apparently, is not indifferent to whether things are known. What that means precisely, what it means is at the level of interpretation, at the level of what is really happening to the electron before measurement, at the level of what the wave function actually is where the agreement ends and the quiet, ongoing argument begins. An argument conducted in papers and conference talks and late conversations in university corridors, civil and unresolved and very much still running. The pattern on the screen is clear. The story behind the pattern is not, and may not be for some time or possibly ever, in the way that some questions are not so much unsolved as they are too close to the foundations to be answered from within the structure they support. Start with the assumption that information, once created, stays created. That feels right. It matches experience. If you write something down and then burn the paper, the information is gone in any practical sense. You can't read it anymore, can't recover it without enormous effort. But at the level of physics, the information is still there, encoded in the precise arrangement of smoke molecules and ash particles and heat distributed into the surrounding air. In principle, if you could track every single particle in the room, you could reverse engineer what the paper said. The information didn't vanish, it dispersed, it became inaccessible, but it persisted somewhere in this physical state of the world. This is a real principle. It's called unitarity, in the language of quantum mechanics, and it says that quantum evolution is reversible, that information is never truly destroyed by the equations of motion, only scrambled, only spread thin across more and more degrees of freedom, until recovering it becomes not impossible in principle, but impossible in practice. So when a which path detector registers which slit an electron used, and the interference pattern disappears, the natural assumption is, that's it. The information exists. It's out there. The superposition is broken and the breaking is permanent. The electron has been observed, and observation in this sense is a one-way door. But it isn't quite. The quantum erasure experiment starts from a question that sounds almost childish when you say it plainly. What if you deleted the which path information after recording it, but before looking at the results? What if the detector registered the path and then the record was erased, actually physically erased, scrambled back into a state that could not tell you which way the electron went, before anyone examined the screen? Would the interference come back? The answer, which has been confirmed experimentally in multiple different implementations since the early 1980s, is yes. Under the right conditions, with the right kind of erasure, the interference pattern returns. Not for all the electrons, not in a way that's visible if you look at the full data set without sorting it, but for specific subsets of electrons, the ones whose which path information was successfully erased. The interference is there, unmistakably, precisely, with the same fringe spacing and the same dark bands, as if no measurement had been attempted at all. The erasure gave back what the measurement took away. The setup that made this concrete, the one worth holding in mind, involves a source that produces pairs of particles, quantum mechanically entangled with each other. One particle from each pair, call it the signal photon, goes through the double slit apparatus and heads toward the detection screen. The other particle from the pair, the idler photon, goes in a different direction entirely toward a separate detector arrangement that can either reveal or erase witch path information. The signal photon goes through the slits. It lands on the screen. A dot is recorded. That's the first half of the event. The idler photon, meanwhile, travels its own path and eventually hits one of several detectors. Some of those detectors are arranged to tell you which slit the signal photon went through. Because the two particles are entangled, a measurement on one gives you information about the other. Other detectors in the arrangement are designed to erase that information, to receive the idler photon in a way that makes it impossible, even in principle, to determine which path the signal photon took. When you sort the signal photon hits by which idler detector fired, when you look only at the signal photons whose partners hit an erasing detector, you see interference fringes. When you look at the signal photons whose partners hit a witch path revealing detector, you see no interference, two bands, particle-like, exactly as expected. The same screen, the same signal photons, the same slits. Two completely different patterns depending on what happened to a different particle in a different location after the signal photon had already landed. This is the part that takes the longest to absorb, and I want to stay with it rather than rush past it toward explanation. Because the explanation, while real, while correct, while important, can obscure how genuinely strange the raw result is. You have a photon that has already hit the screen. Its dot is already recorded. And whether that dot is part of an interference pattern or part of a two-band distribution depends on what happened to its entangled partner somewhere else, possibly afterward and in time, in a different part of the apparatus entirely. The interference doesn't show up in the raw data on the screen. You can't look at the screen alone and see fringes. You only see the fringes when you correlate the screen data with the idler detector data, when you sort the signal photons into subgroups based on what their partners did. It's in the correlations that the pattern lives, not in any individual photon's behavior. But the correlations are real. The fringes in those sorted subgroups are real, and the fact that they depend on what happened to the idler photon, including whether the idler photon's information was erased, is real, confirmed, and has not gone away under any experimental scrutiny. Now, the question that the quantum eraser almost seems to raise, the one that floats up from the result and is very hard to push back down, is whether the erasure is happening backward in time, whether the signal photon, having already landed on the screen, was somehow retroactively given back its interference capacity by what the idler photon did later. And this is where I want to be careful, because the temptation to say yes, retroactively, is strong and also wrong. Or, not exactly wrong, but pointing in a direction the physics doesn't actually support. The signal photon's behavior is fixed when it lands. The dot is where it is. What the erasure changes is not the past behavior of the signal photon, but the correlations, the relationships between signal photon outcomes and idler photon outcomes that become visible only in the combined data. No information travels backward in time. No signal is sent from the idler detector back to the signal photon before it lands. The fringes only appear when you already have both datasets and you sort them together, which requires the idler measurement to be complete, which means nothing about the future of the experiment can influence the past of it in any operationally meaningful way. Quantum mechanics is very careful about this. The no communication theorem, which is a real theorem with a real proof, says that quantum entanglement cannot be used to send information faster than light or backward in time. The correlations are real. The information transfer is not. And yet, the result still has the texture of something that doesn't fully sit still. Not because it violates any theorem, but because the theorems feel like they're describing the shape of a cage without explaining what's inside it. The no communication theorem tells you what can't happen. It doesn't tell you what is happening at the level of what the wave function is, what the entanglement means physically, why the correlations exist in the form they do. What the quantum erasure actually demonstrates, stripped of the time travel framing that tends to attach itself to popular descriptions of it, is something more precise and, in its own way, more interesting. It demonstrates that the relevant variable governing interference is not whether a measurement happened, it's whether which path information is available in the final state of the universe, in the combined state of the signal photon, the idler photon, and every system they've interacted with. If that final state contains recoverable which path information anywhere, no interference. If the which path information has been genuinely scrambled, genuinely made unreadable by the erasure, the interference is recoverable in the correlations. The universe isn't tracking whether you looked, it's tracking whether the information exists to be looked at. An erasure, real, physical, irreversible scrambling of the which path record, gives back the interference not because it changes the past, but because it changes what the present state of the system contains. What is knowable, what is encoded, what exists in the physical sense as a distinguishable record of which way the electron went. The word knowable is doing an uncomfortable amount of work in that sentence, and I'm aware of that. Knowable to whom? Knowable by what? Knowable under what conditions, using what resources, at what cost? These are not idle philosophical questions. They connect directly to debates about what the wave function is, about what decoherence does, about whether collapse is a real physical process or an artifact of how we describe quantum systems from the outside. Those debates have not been resolved. They are ongoing, and the quantum erasure is one of the experiments that keeps them alive, not by providing an answer, but by sharpening the question, by making it impossible to dismiss the role of information as merely incidental, merely subjective, merely a feature of our description rather than a feature of the physics itself. Start with the assumption that information, once created, stays created. It does. The experiments don't violate that, but they do something almost as strange. They show that the consequences of information, what it does to quantum coherence, to interference, to the behavior of particles that have passed through slits and landed on screens, those consequences are sensitive not just to whether information was created, but to whether it survives. Whether it remains encoded in a form that could, in some physical sense, distinguish one path from another. Erase it thoroughly enough, and the electron behaves as though it was never measured. Not because the past changes, because what the present contains has changed, and the present is what the physics runs on. The sun has fully cleared the horizon now, I think. The light through the trees looks different, warmer, less tentative than it did an hour ago. The park is the same park, but with more colour in it. The same grass, the same hedges, the same empty benches, but something about it is different because the light is different, and the light is different because the source of it has moved. The electron doesn't know what time it is. It doesn't experience the experiment. It exists in whatever state the physics places it in, constrained by whatever information the universe currently holds about its path, and it lands where the probability says it most likely will. Somewhere on the screen, a dot, and somewhere else in the apparatus, its partner, the idler, the other particle from the entangled pair, heading toward detectors that will either keep or erase the record of which way the first one went. Both particles already moving, the erasure already in progress or not, and the pattern on the screen already accumulating, already being sorted by correlations that won't be examined until later, until both halves of the data are in hand and someone sits down with the combined record and begins to look. What they find will depend on what was erased. What was erased will depend on how the apparatus was set up, and how the apparatus was set up will determine, in a way that is not mystical but is genuinely not fully understood, what the electron was allowed to do. The air is full of information, not metaphorically, physically. Right now, wherever you are, the air around you is carrying an extraordinary density of correlations, photons that have bounced off surfaces and carry the shapes of those surfaces encoded in their polarization and momentum. Thermal radiation emitted by every object in the room at a rate determined by its temperature. Sound waves that have reflected off walls and still hold faintly the structure of whatever produced them. The air is not empty space between things. It is a medium saturated with the physical consequences of everything that has happened in the room recently. A record, distributed and largely unreadable, but a record. This is what the electron encounters when it leaves the controlled environment of a careful laboratory and enters anything resembling the ordinary world. Not a detector, not a conscious observer. Just air, molecules, thermal noise, the ordinary relentless busyness of matter at room temperature interacting with other matter. And it is enough. More than enough. Decoherence is the name for what happens next, and it is both the most important concept in understanding why quantum behavior disappears at human scales, and somehow one of the most consistently underexplained ideas in popular accounts of quantum mechanics. It tends to appear as a footnote, a technical detail. The part where the narrator says, and this is why we don't see quantum effects in everyday life before moving on to something more dramatic. It deserves more than that. The electron in the double slit experiment maintains its superposition, its spread across both path state, its capacity for interference, because it is isolated, because nothing in its environment has interacted with it in a way that could distinguish which path it took. The coherence of its wave function, that precise phase relationship between the left path and right path components, survives as long as the electron remains, in the relevant sense, alone. The moment it interacts with something, a photon, an air molecule, a stray electromagnetic field, that something becomes entangled with the electron. The electron state and the environment state are now correlated, and the environment, crucially, is not a simple two-state system. It is an extraordinarily complex system, with an astronomical number of degrees of freedom, and the which path information, once it leaks into the environment, spreads through those degrees of freedom almost instantaneously and becomes practically irrecoverable. Not gone, dispersed, spread across so many particles, so many correlations, so many layers of entanglement with other particles that have their own entanglements with others, that tracing it back, reconstructing the original which path record from the environment state, would require a measurement of essentially the entire environment, performed with perfect precision. In practice, this never happens. The information is there in principle. It is gone in practice, and the interference is gone with it. This is the central metaphor this chapter will stay with. Decoherence as a leak, not a catastrophic rupture, a leak. The quantum coherence of the electron, that fragile, precise phase relationship that allows interference, seeps out through every interaction with the environment, spreading into the wider world in a way that is individually tiny and collectively total. A single air molecule bouncing off the electron carries away an almost infinitesimal amount of which path information. The electron's wave function is barely affected by one such collision, but at room temperature, a particle the size of an electron interacts with its environment at rates that make almost infinitesimal irrelevant, because the interactions accumulate so fast across so many degrees of freedom simultaneously that the coherence is effectively gone in a time so short it barely qualifies as a duration. For a large molecule, something like a protein or a grain of dust, the decoherence time at room temperature is somewhere around 10 to the negative 13th seconds. That is 1/10 of 1/trillionth of a second. The coherence doesn't survive long enough to be called brief. It survives long enough to be called effectively non-existent. This is why you don't walk through walls. Not because the quantum mechanics doesn't apply to you, it does in principle all the way up, but because the decoherence time for an object of your mass in an environment of your density is so incomprehensibly small that the quantum behavior is smeared into classical behavior before it can express itself in any measurable way. Your body is in superposition technically. Every atom in it obeyed the quantum mechanics, but the superposition decoheres, leaks into the environment so fast and so thoroughly that the interference terms, the quantum cross terms that would produce genuinely non-classical behavior, vanish. What remains looks exactly like classical probability, not quantum superposition, classical uncertainty. The kind that says the particle went one way or the other, we just don't know which is a completely different claim from the quantum one, but produces the same predictions when the coherence is gone. Decoherence doesn't solve the measurement problem. That's worth being careful about, because it's sometimes presented as if it does. It explains why quantum systems stop behaving like quantum systems when they interact with large, complex environments. It explains why we don't see Schrödinger's cat in a superposition of alive and dead, but it doesn't fully explain why, when we finally look at the cat, we see one outcome rather than the other. It doesn't explain why probability collapses to a single result at the moment of observation, rather than the universe simply continuing to evolve with both results present in some branching structure. That question, what actually happens at the moment of measurement, what selects one outcome from the probability distribution, is the measurement problem, and decoherence addresses the edges of it without touching the center. The machinery of knowing, then, is more distributed than it first appears, is not located in the detector, not in the screen, not in the experimenter's eye. It is in every interaction the quantum system has with its environment, every photon that grazes it, every molecule that passes within range, every field that shifts in response to its presence. All of these are potential witchpath measurements. All of them are potential sources of decoherence. All of them are, in the precise technical sense, observers. The air itself is watching, not consciously, not selectively, just physically, automatically, inescapably. The environment monitors quantum systems by interacting with them, and those interactions leave traces, and the traces destroy coherence, and the destruction of coherence is what makes the quantum world look at human scales, like the classical world. There's a version of this that feels almost relieving. The quantum strangeness doesn't disappear at large scales because of some arbitrary rule about size. It disappears because large things are impossible to isolate, because the environment is always there, always interacting, always carrying information away into its vast and tangled state space. The transition from quantum to classical isn't a boundary, it's a gradient, governed by how strongly a system couples to its environment and how quickly that coupling distributes the witchpath information beyond practical recovery. Small, cold, isolated systems stay quantum longer. Large, warm, complex systems decohere almost instantly. The lab goes to extraordinary lengths to push that gradient. Dilution refrigerators that bring systems to within thousandths of a degree of absolute zero. Vacuum chambers that remove the air that would otherwise carry information away. Electromagnetic shielding that blocks stray photons from the wider environment. All of this engineering, all of this careful and expensive isolation, just to give a quantum system enough time to behave like a quantum system before the environment finds it. It always finds it eventually. I want to say that decoherence explains why particles behave differently when observed, and in a limited but real sense that's true. The environment observing the particle, through thermal collisions and stray photon interactions, is what destroys the interference. But the word ixms is doing something slightly dishonest there, or at least slightly incomplete, because what decoherence describes is the mechanism of the transition without fully accounting for what the transition is a transition to. The formalism is clear. The interpretation underneath the formalism is not. And that gap between the clarity of the mathematics and the murkiness of what the mathematics is describing is the place where physicists have been sitting, with varying degrees of comfort, for nearly 100 years. The machinery of knowing is real. Its parts are identifiable. The environment entangles with the system, the coherence leaks. The interference terms vanish. The classical probability distribution remains. Each step follows from the last. What is less clear, what remains after all the steps are laid out stubbornly unclear, is what it means for the environment to know something. Whether the entanglement between the electron and the air molecule that bounced off it constitutes in any meaningful sense an observation. Whether observation is a property of the interaction or of the system doing the interacting or of the information that survives it. Whether, when the air carries away the witch path record, something like knowing has actually occurred. The park is quieter than it was earlier, or maybe just differently quiet. The birds have started, so the silence has texture now, has interruptions, has a rhythm that makes the pauses between sounds feel more deliberate than they did in the early flat stillness of an hour ago. The light is different too, yellower, lower and coming from a direction that makes the dew on the grass visible as a kind of surface shimmer, each drop catching and bending the light in its own small way. Every one of those drops is in thermal equilibrium with the air, exchanging photons, radiating heat, interacting with its environment at a rate that would decohere even a moderately sized quantum system in a time too small to name. The grass doesn't know this. The dew doesn't know this. The physics runs anyway. There is a version of quantum mechanics in which nothing ever collapses. The wave function, that mathematical object encoding everything that could happen to a quantum system, simply evolves, always, continuously. According to the Schrödinger equation, without interruption, without exception, without any special event called measurement that causes it to suddenly become one thing instead of many. In this version, when an electron hits a screen, the screen doesn't register one outcome. The screen enters a superposition of registering all outcomes simultaneously. And when an experimenter looks at the screen, the experimenter doesn't see one result. The experimenter enters a superposition of seeing all results simultaneously. Everything that could happen, happens. All of it. Always. This is the many worlds interpretation proposed by Hugh Everett in 1957 in a doctoral thesis that was largely ignored for 2 decades and has since become one of the most seriously discussed and most deeply divisive frameworks in the foundations of quantum mechanics. I'm walking back from the park now. The morning has warmed slightly, not enough to matter, but enough to notice. My shoes are damp from the grass. The city is beginning to move around me, engines and distant voices, the ordinary sound of a day starting. I find I think more clearly when I'm moving. Something about the shift from sitting to walking that makes certain ideas easier to hold. Everett's proposal didn't start from dissatisfaction with the predictions of quantum mechanics. The predictions were fine. They remain today the most precisely verified predictions in the history of science. His dissatisfaction was with the story being told alongside the predictions. With the Copenhagen interpretation's insistence that the wave function collapses at measurement, that there is a sharp boundary between quantum systems and classical measuring devices, that the observer occupies some special role outside the formalism. That boundary, Everett felt, was a cheat, an addition to the theory that the theory itself didn't require or justify. If the Schrödinger equation is correct, and all evidence says it is, then it should apply to everything, including the measuring device, including the experimenter, including the entire universe. And if it applies to everything, then collapse, that sudden, probabilistic one-outcome selected event, has no place in the equations. It was added to make the theory match experience. But maybe, Everett suggested, the experience could be derived from the theory without adding anything. Maybe the appearance of a single outcome, the reason an experimenter always sees one result, never a superposition, could be explained by the wave function branches when a quantum system interacts with a macroscopic one. You are in the branch where the electron went left. Somewhere else, in a structure just as real, the version of you who is identical in every way up to this moment sees it go right. The branching is not a choice. It's not dramatic. It happens at the moment of entanglement between the quantum system and whatever it interacts with, and it happens according to the same smooth deterministic evolution that governs everything else. The branches don't communicate with each other after they separate. They can't. Decoherence ensures that the interference terms between them become practically zero, almost instantly and without interference. The branches have no way to affect each other. They become, for all practical purposes, separate worlds. Hence the name, many worlds, many branches, one wave function. In this framework, the particle doesn't know it's being watched because there is no watching. Not in the sense of a collapse triggered by observation. There is only entanglement. The particle interacts with the detector interacts with the environment interacts with everything else, and the wave function of the whole system branches into components where each possible outcome is realized in some branch. No special event, no privileged moment, no observer required beyond the physical fact of interaction. The interference pattern disappears not because the electron collapsed to one path, but because the which path information is now encoded in the wider state of the system, detector, environment, everything, and the branches where the electron took the left path and the branches where it took the right path have decohered to the point where they can no longer interfere. The math is the same as before. The interpretation underneath the math is entirely different. No collapse, no randomness at the fundamental level. Just branching, just the wave function doing what it always does. This is, on its face, a staggering claim. An infinite, or at least an enormously large proliferation of branches, each containing a full copy of the universe, each equally real, splitting at every quantum event, at every point in space, at every moment. The extravagance of it is hard to overstate. You are in this framework constantly branching. Every quantum event in your body, every photon absorbed by a rhodopsin molecule in your retina, every radioactive decay in the potassium atoms in your cells, produces a branching of the wave function and a corresponding branching of you. The you reading this is one branch among an incomprehensible number. The immediate objection is, where are they? Why don't we experience them? Why does it feel definitively and without ambiguity like there is one world? And the answer, the many worlds answer, is that it would feel exactly like this. In every branch, the version of the experimenter who exists there experiences exactly one outcome, because that branch contains a world where exactly one outcome occurred. The other branches don't feel like anything to you because you are not in them. You're here. The others are equally real, equally inhabited by versions of you having equally singular experiences, and none of you can see the others. The honest thing to say about this is that it is internally consistent and deeply unsatisfying in ways that are difficult to fully articulate. The internal consistency is genuine. Many worlds quantum mechanics makes no predictions that differ from standard quantum mechanics. It produces the same numbers, the same probabilities, the same experimental outcomes. It doesn't add collapse, but it doesn't need to. because the appearance of collapse is derived from the branching structure and the decoherence that separates the branches. The math works, the theory is coherent, the dissatisfaction is harder to pin down. Part of it is the proliferation, the sheer staggering excess of reality the theory requires. Part of it is the probability problem. In a theory where all outcomes happen, it is surprisingly difficult to recover a rigorous account of why some outcomes seem more likely than others, why the Born rule probabilities match experience. Part of it is something more personal than either of those, something about the claim that all possibilities are equally real that sits in a way that no amount of mathematical consistency entirely settles. No, actually, that's not quite what bothers me. It isn't the many worlds, it's the manyness of the you that bothers me, on reflection. The idea that the experience of being a singular observer, having singular experiences, is not a fundamental feature of reality, but a local artifact of which branch you happen to be in. That might be true. The theory doesn't give you a way to know. What many worlds does, what makes it worth sitting with, whatever its difficulties, is remove the observer from the centre of the story. In Copenhagen, the observer is necessary. The collapse requires an observation. The boundary between quantum and classical requires someone or something on the classical side to perform measurements. In many worlds, the observer is just another physical system, entangling and branching like everything else, with no special role and no special power. The particle doesn't know it's being watched, because being watched is not a distinct event. It's just an interaction, just entanglement, just the wave function evolving. The strangeness doesn't go away in this picture. The interference disappears for the same reason it disappears in any other interpretation, because the witch path information has spread into the environment and the branches have separated. But the strangeness is redistributed. Instead of living in the mystery of collapse, in the question of what causes the wave function to suddenly select one outcome, it lives in the proliferation of branches, in the question of what it means for all of them to be real, which is a different mystery, not a smaller one. There are other interpretations, many of them. Pilot wave theory, which Chapter 10 will spend time with. Relational quantum mechanics, which holds that quantum states are not absolute but relative to particular observers. Cubism, which treats the wave function as a representation of an agent's beliefs, rather than an objective feature of the world. Each of them resolves the measurement problem differently. Each of them relocates the strangeness rather than eliminating it. Many worlds relocates it into ontology, into the question of what exists, into the proliferating structure of a universe that contains every possibility and calls all of them real. Whether that is a cost or a feature depends, I think, on what you find more uncomfortable. A universe that selects outcomes through a process we don't understand, or a universe that never selects anything and simply contains all outcomes simultaneously in branches you'll never visit. Both options are strange. The second is stranger in a way that is, oddly, almost restful. Because if all possibilities are real somewhere, then the question of which one is the right one dissolves. There is no right one. There is only the branch you're in, which feels from the inside exactly like the only one. The word was always too big for the job it was given. Observer. It sounds like it requires a presence, a mind behind an eye, something that registers, that processes, that understands what it's looking at. In ordinary language, the language of courtrooms and scientific papers and everyday conversation, an observer is someone who watches, someone present, someone capable of taking in information and doing something with it. Quantum mechanics borrowed the word and never fully explained what it meant by it. That borrowing has caused, quietly and persistently, more confusion than almost any other terminological decision in the history of modern physics. In Chapter 5, we left something deliberately unresolved. The word observer was placed on the table and then not fully examined, not because the examination wasn't possible, but because arriving at it too early would have flattened something that needed more space to develop. The question was, what does it actually mean, physically, for something to count as an observation? Whether the word observer requires anything like a mind, or whether its meaning in quantum mechanics is something altogether more mechanical, more distributed, more indifferent to consciousness than the word itself suggests, this is where that thread gets picked up. In the earliest formulations of quantum mechanics, Copenhagen broadly, the language was genuinely ambiguous. Bohr wrote about the role of the observer in ways that could be read as implying consciousness mattered. Von Neumann's mathematical formulation of quantum mechanics included a chain of measurements that seemed to terminate ultimately in the conscious experience of an observer. Wigner, a Nobel laureate and a serious physicist, proposed explicitly that consciousness caused collapse, that the wave function remained in superposition until a mind registered the outcome. This was not fringe thinking at the time. It was a reasonable response to a genuine problem. The mathematics didn't specify where in the chain from quantum system to measuring device to experimenter's brain the collapse occurred. So some physicist located it at the only place that seemed categorically different from everything else in the chain: consciousness. The problem with this, and it is a serious problem, not just a philosophical quibble, is that consciousness is not defined in the physics. It has no equation, no measurable property, no agreed upon physical signature. Inserting it as the trigger for wave function collapse doesn't solve the measurement problem. It relocates the mystery into something even less tractable. What the experiments actually require, and this is where the physics speaks more clearly than the philosophy, is something considerably less exotic. Any physical system that ends up in a different state depending on which path the particle took functions, in the operationally relevant sense, as a which path detector. That's the whole definition. Different state for left path, different state for right path. That's a detector. It doesn't need to be connected to anything. It doesn't need to display a readout. It doesn't need to be large or sophisticated or manufactured by humans. A single atom that absorbs a photon scattered off the electron and ends up in an excited state is, in this sense, a detector. The air molecule that bounces off the particle and carries away directional information is a detector. The thermal radiation field that is perturbed differently depending on which slit the electron used is a detector. The environment is full of detectors. They are everywhere. They operate continuously and automatically, and with complete indifference to whether any mind is present to interpret their states. This is the operational answer to what an observer is. An observer is any physical system that becomes correlated with the path of the quantum system. Any system that transitions into states that are distinguishable depending on what the quantum system did. It does not require eyes, it does not require a brain, it does not require the capacity to understand or process or remember. It requires only that the correlation exists, that the system's state carries in some physical form information about which path was taken. A rock in principle could be a detector, a cloud of gas, a fluctuation in a magnetic field. The requirement is correlation, not cognition. Now, this answer is clean and it is correct, and it resolves the confusion in a way that is genuinely useful, and I want to say all of that plainly. But I also want to be honest about what it doesn't resolve, because pretending the question is fully closed would be its own kind of distortion. The operational answer tells you what functions as an observer, what produces the which path information, what destroys the interference. It doesn't tell you what observation is. at the level of what is actually happening to the wave function when the correlation is established. Whether the wave function collapses, actually physically transitions from a superposition to a definite state, or whether it branches into many worlds components that decohere and separate, or whether it was never a real physical object to begin with, and the whole question is malformed. These are not answered by identifying what counts as an observer. The operational definition sidesteps the measurement problem rather than solving it, and the measurement problem is still there, behind the clean language, unresolved. There is a view, associated most strongly with the Copenhagen interpretation, though it predates the name, that asking what happens to the wave function during measurement is simply the wrong kind of question, that the wave function is a calculational tool, not a description of physical reality, and that demanding an account of what it physically does during collapse is like demanding an account of what a probability distribution physically does when the dice land. The dice land. The probability distribution updates. Nothing happened to it in a physical sense. It was never a physical thing. On this view, the observer is whoever is using the formalism, whoever is making predictions and comparing them to outcomes. The wave function is relative to that user, updated when they acquire new information, and the question of what counts as an observation is just the question of when the user updates their probability assignments. This is tidy. It avoids the metaphysical tangles. It also, to my mind, evades more than it resolves, because it places the physics inside the heads of physicists. And the universe was running quantum mechanics for 13 billion years before any physicists existed to calculate anything. That objection doesn't refute the view, just makes me uncomfortable with it. The more physical answer, the one that takes the wave function seriously as a real object and asks what really happens to it, leads inevitably back into the interpretational swamp. Collapse theories, many worlds, pilot waves, relational quantum mechanics, each carving the problem differently, each relocating the strangeness without eliminating it. What they agree on, the narrow strip of consensus, is exactly the operational point. The witch path information, encoded in the physical state of any system correlated with the particle's path, is what governs whether interference survives. Consciousness is not in that sentence. Mind is not in that sentence. The presence or absence of a human being in the lab is not in that sentence. Observer, in quantum mechanics, means correlated physical system. It is a mundane definition for a word that accumulated an enormous amount of non-mundane implication. The implication was never licensed by the physics. It arrived through language, through the ordinary meaning of a word pressed into service in a domain where its ordinary meaning didn't apply. The confusion was not stupid. It was almost inevitable, given the historical sequence, given that the people working out quantum mechanics in the 1920s and 1930s were using the conceptual tools available to them, which included a word, observer, that carried human weight. The wonder is not that the confusion arose, the wonder is that it persisted as long as it did, and still persists in popular descriptions of the theory, trailing its implications about consciousness and the primacy of the mind through decades of science writing and documentary narration. The electron doesn't know it's being watched. It doesn't know anything. It has no interiority, no sensitivity to the presence of minds, no mechanism by which the arrival of a conscious observer could affect its behavior differently from the arrival of an unconscious one. What it is sensitive to, exquisitely, precisely, without exception, is whether the physical world contains a record of which way it went. Not who made the record, not whether anyone will read it, just whether it exists. That is a strange enough thing on its own. It doesn't need the additional strangeness of consciousness to be remarkable. There was another way. That's worth sitting with for a moment before anything else. because by the time most people encounter quantum mechanics, in textbooks, in lectures, in the kind of late-night reading that leads to videos like this one, the Copenhagen interpretation is already there, already installed, already presented as the framework rather than a framework. The wave function, superposition, collapse, the uncertainty principle. These arrive packaged together as if they were the only available response to the experimental results, as if the strangeness of the data left exactly one exit. It didn't. Louis de Broglie proposed something different in 1927 at the Solvay conference, in front of the people who were in the process of building the version of quantum mechanics that would become standard. He called it pilot wave theory, and the basic idea was, because the theory is still alive, still developed, still taken seriously by a small but serious community of physicists, that the electron is always a real particle with a real position, following a real trajectory through space, always somewhere definite, never in superposition in the sense of being nowhere in particular, but it is guided, carried, pushed along its path by a wave, a real physical wave, propagating through space, obeying its own equation, passing through both slits simultaneously, while the particle passes through only one. The particle surfs the wave tells the particle where to go. That's the picture, or close enough for now. I've been at this for a while now. The apartment is warmer than the park was, which helps, though the light in here is flatter, overhead, slightly yellow. The kind of light that's fine for working but not particularly kind to thinking. There's coffee going cold on the desk. I keep meaning to drink it. Anyway, the interference pattern in de Broglie's picture is not mysterious. It's exactly what you'd expect. The wave passes through both slits. The two portions of it interfere on the far side of the barrier. Real wave interference, exactly like water, exactly like sound, and the resulting wave structure has peaks and troughs. The particle riding the wave is steered away from the troughs and toward the peaks. Over many electrons, each riding its own pilot wave, the distribution of landing positions follows the wave's intensity pattern. Fringes, interference, explained entirely by the wave without the particle ever being in two places at once. The particle was always somewhere. The wave is what was everywhere. This resolves, or seems to resolve, one of the most persistently uncomfortable features of Copenhagen quantum mechanics, the apparent non-locality of the wave function, the sense in which the electron is genuinely spread out across both paths until measurement forces it to choose. In pilot wave theory, the electron's never spread out. It is always local, always a point in space, always on one side of the apparatus or the other, following a deterministic trajectory determined by the wave. What's non-local is the wave. The pilot wave is, in the technical sense, a non-local object. Its behavior at any point depends on the global configuration of the entire system, instantaneously. This non-locality is what allows it to account for quantum correlations, for entanglement, for the results that seem to require spooky action at a distance. The wave knows about the whole setup. The particle follows the wave. You trade the non-locality of the particle for the non-locality of the wave. Whether that's a resolution or a relocation of the problem depends on what you found troubling in the first place. Which path measurement, in this framework, works differently than in Copenhagen, but arrives at the same result? When a detector is placed near one of the slits, it interacts with the pilot wave. The wave, the real physical wave that was about to produce interference, is disturbed by the interaction, not destroyed, altered. The two portions of the wave, the left slit portion and the right slit portion, become entangled with the detector's degrees of freedom in such a way that they can no longer interfere with each other effectively. The interference requires the two wave portions to be coherent, to maintain their phase relationship, and the interaction with the detector breaks that coherence, much as it does in any other interpretation. The particle, still riding the wave, now finds itself on a wave that no longer has interference structure, so it lands somewhere consistent with a two-band distribution. No fringes, same result, different story. The theory was presented at Solvay and met with a reaction that ranged from skeptical to dismissive. Pauli raised objections. Bohr was characteristically difficult to pin down on specifics but broadly unconvinced. And de Broglie, who was not yet 30 and was surrounded by the architects of the Copenhagen framework, withdrew the idea, didn't publish it in developed form, set it aside. It sat for 25 years. Then David Bohm, working independently and apparently without full knowledge of de Broglie's earlier attempt, reconstructed the theory in 1952 and published it in 2 papers in Physical Review. He called it a causal interpretation of quantum mechanics, meaning that quantum events had definite causes, the pilot wave, rather than being irreducibly probabilistic. The reaction from the establishment was, again, largely dismissive. John Bell, who later did the work on quantum correlations that bears his name, and who was one of the more careful thinkers in the foundations of quantum mechanics, wrote that the pilot wave theory was ignored for reasons that were more sociological than scientific. The formalism worked. It reproduced every prediction of standard quantum mechanics exactly, without exception. It added something, the definite particle position, the pilot wave, but it subtracted something too, the need for collapse, for special observers, for the uncomfortable duality between quantum systems and classical measuring devices. The cost is the wave. The pilot wave is a strange object. It propagates in configuration space, not in the three-dimensional space we inhabit, but in the full space of all possible configurations of the system, which grows in dimension with every additional particle. For a system of 2 particles, configuration space is 6-dimensional. For a system of 1 trillion particles, it is 3 trillion dimensional. The wave lives there in that high-dimensional space, and the particles in ordinary 3-dimensional space follow it. This is not physically impossible, it is physically awkward. The pilot wave doesn't quite feel like a normal physical field. It doesn't carry energy in the conventional sense, doesn't propagate at a finite speed through space, exist in a space that is more mathematical than physical in its texture. Whether it is real, in the same sense that an electromagnetic field is real, is something pilot wave theorists disagree about. Some say it is real and physical, and we need to get comfortable with configuration space as the fundamental arena of physics. Some say it is a convenient fiction that makes the math work and the particle positions real. Some say, and this is perhaps the most honest position, that the question of what it is at the deepest level is still open. There are objections, several serious ones. Relativistic quantum mechanics, quantum field theory, the framework that describes particles at high energies and gives us the standard model, has not been fully reconciled with pilot wave theory. The extension exists in partial form, but it is technically difficult and not universally accepted as satisfying. Pilot wave theory is more naturally a theory of particles than of fields, and the world at its deepest accessible level is a world of fields. There is also the matter of the quantum equilibrium hypothesis. Pilot wave theory reproduces the statistical predictions of quantum mechanics, the Born rule probabilities, only if the initial distribution of particle positions satisfies a particular condition called quantum equilibrium. The theory provides arguments for why this condition should hold, drawing on analogies with statistical mechanics and thermodynamic equilibrium. Those arguments are reasonable. They are not entirely airtight, and there is something that I keep returning to, something that might be a preference rather than a principle, The pilot wave theory restores determinism and definite particle positions, but it does so by adding a wave that is, in some ways, more mysterious than the thing it replaces. You've traded one puzzle for another. The puzzle is different in character. It feels more like a classical puzzle, more like something we might eventually understand through familiar physical reasoning. But whether that familiarity is genuine illumination or just a more comfortable kind of darkness is not obvious. I genuinely don't know. I think that's the honest answer. What pilot wave theory does, regardless of whether it is ultimately the right picture, is demonstrate something that gets obscured when Copenhagen is treated as the only available response to quantum mechanics. It demonstrates that the same experimental results are compatible with multiple underlying stories, that the data underdetermines the theory, that choosing between interpretations is not at present a matter of experiment, it is a matter of which metaphysical furniture you find most livable. Particles that are always somewhere, guided by waves they don't know about, or particles that are nowhere definite until measured, or particles that are everywhere at once in all branches of a proliferating wave function. The experiments so far cannot distinguish between these pictures. They are empirically equivalent, which means the question, what is the electron really before it lands, is still open, genuinely, stubbornly, possibly permanently open. De Broglie sat in that Solvay conference room in 1927, surrounded by the people who were building the future of physics, and proposed a wave that guided a particle that was always real and always somewhere. And the room was skeptical, and he set the idea aside, and 25 years later Bohm picked it up again from a different direction and found it still worked, still reproduced everything, still offered a different way of seeing. The pilot wave moves through both slits. The particle moves through one. The interference is in the wave. It's a strange comfort, maybe, or not quite a comfort, more like the feeling of finding a path you didn't know existed. It doesn't necessarily go where you want to go, but it's there. It was always there, and knowing it exists changes slightly the texture of the territory. An atom in a gas doesn't wonder where it is. That sounds obvious. Of course it doesn't wonder. It's an atom. It has no capacity for wondering, no interiority, no perspective from which a question could even form. But the obvious point conceals a less obvious one, which is that the atom doesn't just lack the capacity to wonder where it is, it lacks a definite where. Not because we haven't measured it, not because our instruments are too coarse, because in the quantum mechanical description of the world, the position simply isn't there to be found until something interacts with the atom in a way that forces a definite location to manifest. The blur is not ignorance. The blur is the state. This is the part of quantum mechanics that resists the longest. The uncertainty principle, Heisenberg's the real one, not the popular misstatement of it, is often described as a limitation on measurement. You can't know the position and momentum of a particle simultaneously because measuring one disturbs the other. That framing is not entirely wrong, but it undersells what the principle is actually saying, which is something more radical. The position and momentum of a quantum particle are not simultaneously definite. There is no hidden, precise value for both that we simply fail to access. The definiteness isn't there. The particle doesn't have a precise position and a precise momentum that exist together, waiting to be found. It has a wave function that assigns probability amplitudes to ranges of position and momentum, and those amplitudes are related by a mathematical constraint, the Fourier relationship between position and momentum space, that makes it impossible for both to be sharply defined at the same time, even in principle. This is not a measurement problem. It is an ontological one. The atom in the gas doesn't know where it is because, though in any complete quantum description, It doesn't have a where in the classical sense. It has a probability distribution, a spread of possible positions weighted by the square of the wave function's amplitude, that describes not our uncertainty about the atom's location, but the atom's actual physical state. At room temperature, for a light atom like hydrogen, the thermal de Broglie wavelength, the characteristic spread of the atom's wave function, is on the order of a fraction of a nanometer. Small but non-zero. The atom is quantum mechanically spread across that distance in a way that is physically real. At lower temperatures the spread grows. Cool a gas of atoms close to absolute zero, and the thermal de Broglie wavelength increases until it becomes comparable to the spacing between atoms. At that point the wave functions of individual atoms begin to overlap, and something extraordinary happens, something that is, in its quiet way, one of the most striking demonstrations of quantum mechanics operating at scales large enough to see. The atoms stop being individual atoms, Bose-Einstein condensation. Predicted by Satyendra Nath Bose and Albert Einstein in 1924 and 1925, observed in the laboratory for the first time in 1995 by Eric Cornell and Carl Wieman, using a gas of rubidium atoms cooled to about 170 billionths of a degree above absolute zero. The Nobel Prize in Physics followed in 2001. At that temperature, the individual wave functions of the rubidium atoms overlap so completely that the atoms lose their separate quantum identities and collapse, not in the measurement sense but in the spatial sense, into a single collective quantum state. Thousands of atoms occupying the same quantum state simultaneously, behaving as a single coherent object. A new phase of matter, not solid, not liquid, not gas, something that has no classical analogue, no intuitive picture, no everyday equivalent to reach for. A cloud of atoms the size of a few micrometers, cold enough that the quantum blur of each individual atom has grown large enough to swallow the distance between them, until the distinction between one atom and the next becomes physically meaningless. The atoms don't know they've done this. They don't coordinate. They don't decide. The condensation is what happens when the quantum statistics of identical particles, the fact that bosons, unlike fermions, can and in fact prefer to occupy the same quantum state, combine with temperatures low enough that thermal agitation stops overwhelming the quantum correlations. It happens because the physics requires it to happen. The connection to everything this video has been circling is this. The Bose-Einstein condensate is a system in which quantum coherence, the kind of fragile, precise phase relationship that the double-slit experiment depends on, that decoherence destroys almost instantly in warm environments, is maintained across thousands of atoms simultaneously at scales large enough to photograph. It is quantum mechanics made visible, not inferred from statistics on a screen. Directly, photographically visible as a sharp peak in the density of the atomic cloud, a sudden condensation from a broad thermal distribution into a tight, coherent clump that is the spatial signature of all those atoms occupying the same quantum state. The which path problem in a Bose-Einstein condensate takes on a different texture. The atoms are indistinguishable, genuinely, physically indistinguishable, not just similar but identical in the quantum mechanical sense, meaning there is no fact of the matter about which atom is which. The question of which path a particular atom took through a particular region of space has no answer, not because we failed to measure it, but because the question assumes individuality the atoms don't possess. There is no particular atom to track. There is only the condensate, the single collective wave function, evolving as a whole. You cannot ask which atom went left and which went right. The question doesn't have a referent. This is, perhaps, the cleanest version of the idea that has been running through this video since the beginning. The idea that the electron's behavior when watched, is not about watching in any human sense, but about whether the physical world contains information that could, in principle, distinguish one path from another. In the condensate, the indistinguishability of the atoms is so complete, so built into the quantum statistics, that the very notion of distinguishing paths is undefined. The interference, when condensates are split and recombined in interferometry experiments, is total, perfect, because there is nothing nowhere in the physics that constitutes a witch path record. No record, full interference. The atom doesn't know where it is, and in the condensate the collection of atoms doesn't know where any of them are, because the question of where each one is has dissolved into the collective wave function that describes them all at once. Here is where a metaphor arrives, and I want to use it carefully because it is imperfect in the way all metaphors are imperfect, useful up to a point and then misleading if pushed further. Think of it like a chord. A single note is localized. It has a pitch, a source, a specific string or column of air vibrating at a specific frequency. Multiple notes played simultaneously produce a chord, and the chord is not a collection of separate notes that happen to coexist. It is a new thing. Its character emerges from the relationships between the notes, from the interference between their frequencies, from the way they combine. You can, in principle, analyze a chord back into its component notes, but while you're hearing it as a chord, it is not usefully described as several separate things. It is one thing with the internal structure. The condensate is something like that. Many atoms, one quantum state. Not several separate particles in the same place, but a collective entity whose properties belong to the whole and not to any part of it. The metaphor breaks where metaphors usually break. The chord is made of notes that remain in some sense individual. Each string is still vibrating independently, and we call it a chord only as a description of their combined effect. The condensate atoms are not individually vibrating in independent states that we choose to describe collectively. Their individuality is genuinely physically absent. The collective description is not a choice, it is what is actually true. What the atom doesn't know, then, is not just its position. It doesn't know its momentum with arbitrary precision. It doesn't know, in the condensate, which atom it is. It doesn't know, if we follow the logic all the way, whether it's being watched, because knowing requires distinguishability, and distinguishability requires information, and at the temperatures where quantum coherence persists across macroscopic scales, that information doesn't exist in the environment in any recoverable form. The watching requires something to watch, an individual particle with a definite path, a system with internal states that could, in principle, carry witch path information out into the world. When those conditions aren't met, when the atoms are indistinguishable, when the temperature is low enough that decoherence hasn't yet done its work, when the wave functions overlap and the collective state is coherent, the watching doesn't happen, can't happen, not because nobody tried, because the physical prerequisites for it aren't present. The interference survives not because no one looked, but because there was nothing singular enough to look at. There is something almost restful in that. At this hour, in this apartment, with the coffee long since gone cold and the morning having fully arrived outside, the atom in its blur, the condensate in its collective state, the wave function spreading through both slits, none of it anxious, none of it waiting, none of it aware of the long argument its behaviour has generated. It just does what the physics says it does, in exactly the conditions the physics requires, without knowing any of it. The knowing is entirely on our side of the equation, and maybe that's where it has always been. The question was always a little wrong. Not wrong in the way that bad questions are wrong, or imprecise or lazy, or built on false assumptions that need correcting before anything useful can be said. Wrong in a more interesting way. Wrong the way that certain questions are wrong, that nonetheless lead somewhere real. The kind of wrong that contains, folded inside it, the shape of a better question that you can only see after you've lived with the original one long enough. How does a particle know it's being watched? We started there, hours ago, or what feels like hours. The morning has fully settled into itself now, the apartment light ordinary and flat, the kind of Tuesday that doesn't announce itself as anything particular, and the question is still here. It didn't get answered, exactly, but it changed shape. And the shape it changed into is, I think, more interesting than the original. The particle doesn't know, that much is certain, or as certain as anything in this territory gets. There is no mechanism by which an electron receives information about the presence of an observer and adjusts its behavior accordingly. No signal traveling from the detector to the particle, no quantum channel through which the fact of being watched is communicated. The electron has no interiority, no sensitivity to minds, no way of registering the difference between a conscious observer and an unconscious one. What it is sensitive to is something else, something that took most of this video to approach carefully enough to say without distorting it, the physical state of the world. Specifically, whether the physical state of the world, after the electron has passed through the apparatus, contains information encoded somewhere in some system, in some correlation between states about which way the electron went. Not who holds that information, not whether it will ever be read, not whether it matters to anyone, just whether it exists, in the only sense that exists means anything in physics, whether it is present in the configuration of matter and fields and entangled quantum states that constitutes at any given moment the actual condition of things. If it is there, no interference. If it isn't, the fringes return. That's the answer, or the closest thing to an answer that the physics currently offers, and it is, on reflection, stranger than the original question. Because the original question assumed that the particle was responding to something external, to a presence, to an act of looking, to the arrival of an observer in the vicinity. That framing, wrong as it turned out to be, had the comfort of familiarity. Things respond to other things that interact with them. Causes produce effects. The detector disturbs the electron behaves differently, clean, local, mechanical. The real answer doesn't have that comfort. The real answer says that what the electron responds to is not a presence but a fact, not an interaction, but a consequence of an interaction. The information that remains after the interaction is over, distributed through the environment, encoded in correlations that may be practically inaccessible but are physically real. The electron's behavior is sensitive to the informational state of the universe in its vicinity, which is either a very precise physical statement or a very strange metaphysical one, and the distance between those two descriptions is where the measurement problem lives, unresolved, patient, unlikely to be settled soon. We covered a lot of ground to get here. The double slit experiment, and what the interference pattern actually requires, the witch path measurement, and the discovery that it was information rather than physical disturbance that destroyed the fringes, the quantum eraser, and what it demonstrated about the relationship between erasure and the recovery of coherence, decoherence, and the way the environment functions as a continuous automatic indifferent measuring apparatus that destroys quantum behavior at room temperature almost before it begins, the many worlds interpretation, and what it means to relocate the strangeness from collapse into the proliferation of branches, the pilot wave, and the possibility of a particle that is always somewhere definite, guided by a wave it doesn't know about, surfing interference it didn't create. The word observer, and how much confusion a single borrowed term can generate across a century of physics. The atom in its blur, the condensate in its collective state, the wave function doing what it always does, spreading, evolving, encoding probability in its amplitude, indifferent to whether anything is watching. None of it resolved the question completely. That's not a failure of the physics. That's what the physics currently is. A set of extraordinarily precise predictions sitting on top of a set of genuinely unresolved interpretational disputes that have been running since the 1920s and show no signs of closing. The predictions work every time with a precision that has no parallel in the history of science. The story underneath the predictions is still being argued over, in papers and conference talks and late conversations in university corridors, by people who agree on every number and disagree on almost everything the numbers mean. There's something I find genuinely comforting in that, and I want to say this as an opinion, not as a conclusion the physics licenses, because it doesn't. The physics doesn't care whether you find it comforting, but I do find it comforting in the specific way that unresolved things can be comforting when you've stopped expecting them to resolve. The question of what a particle is before measurement. The question of what measurement is at the level of what actually happens to the wave function. The question of what the universe contains at its most fundamental level. Particles, waves, branches, correlations, information, Sushkan. These questions are open. They have been open for 100 years. The people working on them are serious, careful, mathematically sophisticated, and they disagree. That's not a scandal, that's a frontier. And frontiers are, by definition, the places where the known gives way to something that hasn't been settled yet, where the maps run out and what's beyond them is not nothing but genuinely unknown territory, territory that exists, that has structure, that the equations are already pointing toward, even if nobody has yet worked out what the pointing means. The particle doesn't know it's being watched, but we've been watching it for over 2 centuries now, since Young let sunlight through 2 pinholes in a darkened room and found bands on the wall that shouldn't have been there. And the watching has produced slowly one of the most extraordinary bodies of knowledge in human history. A theory that predicts the behavior of matter at its smallest scales with a precision that extends to 10 decimal places. A theory that underlies the transistor, the laser, the MRI machine, the LED, the solar cell. A theory that is, in any practical sense, the most successful physical theory ever constructed. And that theory at its foundation contains a question it cannot fully answer about what happens when you look. I've been sitting with this for a while now, this particular question, this particular video, and I think the right place to end is not with a summary, not with a neat restatement of everything covered, but with the question itself, left where it is, slightly open, the way it actually is. How does a particle know it's being watched? It doesn't. But something changes when a record exists. Something in the physical state of the world shifts in a way that is mathematically precise and conceptually unresolved when which path information is created. And that shift, that quiet, automatic, consciousness-independent response to the existence of a record, is either a very strange property of matter or a very deep clue about the nature of reality. Maybe both. Maybe the distinction between those 2 things is less clear than it seems at this hour, in this light, with the morning fully underway outside and the apartment quiet and the coffee long since finished. If something here stayed with you, if some part of the question felt like it opened onto something you want to keep thinking about, there's more on the channel. Other questions, other experiments, other places where the physics gets quiet and strange and worth sitting with slowly. And if you know someone who needs this, the slow pace of it, the long form, the kind of science that doesn't rush toward conclusions, send it to them. That's genuinely how this reaches people. One quiet recommendation at a time. Thank you for staying this long, for keeping the question company. Sleep well.